What is an economic model? It's going to be a simplified description of the real world in which we ignore non-essential details in order to focus on those things that matter for the particular question that we are interested in. So a good model might very well be unrealistic. It's going to exclude things that you think matter and are important for explaining the whole variety of behavior. But at the end of the day, by excluding some of those things that might be important to explain details, we're able to make plausible and informative predictions about the future and about the state of the world and other counterfactual scenarios. And this is why we make a model. We make a model to really understand what is happening in human behavior. We make a model to derive predictions so that we can design policies. You want to know, if I do X, what will happen to Y? And that is why economists use models. You've already seen a number of economic models, including the circular flow model, the production possibilities model, the supply and demand model, both positive and negative externality models, the model of perfect competition, and the monopoly model. So some common features of these models include having agents or decision makers who are making decisions that affect outcomes and behavior. Having a choice variable. This is what those agents and decision makers are choosing. You can't simply say, I have an agent and they're going to do stuff. You have an agent who's going to do stuff to a particular choice variable. And we'll walk through some examples. Each choice is also going to have some benefits and costs associated with them. There are going to be some trade-offs that people have to make in order to get a benefit. They have to pay a particular cost. And finally, we'll have a group of variables that we're going to call endogenous and exogenous variables. And I'll define those in a moment. So let's take a look at the supply and demand model and see how it fits into this framework. We'll have agents or decision makers, in this case, consumers and producers. We'll have a choice variable, which is how much to consume for consumers and produce for producers. There will be benefits and costs of these choices, so it'll be consumer or producer surplus. So let's think about consumers in a little bit more detail. I'm going to show you how we write this model mathematically as well. So we're going to maximize by choosing quantity. That's what that max and then Q underneath it means. B of Q minus P times Q. So B is measuring our benefit, and P times Q is the amount of money the consumer has to pay to buy or consume Q units of the good. So we'll call this maximize net benefit by choosing the quantity to consume. For producers, we're going to have a very similar condition. They're going to maximize net profit or producer surplus by choosing quantity. And what they get is price times quantity. They get P times Q, that's their revenue, minus C of Q, and C is their cost. So for producers, we said they maximize profit by choosing the quantity to produce. So now we're in a position to think about what it means for a variable to be exogenous or endogenous. We're going to define exogenous variables as those that are not a function of the choice variable. And endogenous variables are functions of the choice variable. I'm going to highlight all of the endogenous variables in the model in blue. And so we see quantity is endogenous because it is a choice variable itself. And it makes B and C endogenous as well because they are now functions of this endogenous choice variable. I'm going to highlight the exogenous variables in red. In this case, there's only one, P, which is the only exogenous variable in the model. Now let's talk about building your own model. And so there are going to be a number of steps in model building. And the first step is to decide what is the choice variable and who is the decider. And then you need to brainstorm benefits and costs associated with that choice variable for the decider. Not for everyone else, but just for the decider. Then we're going to choose a few to focus in on, just to narrow down the list so we don't have to think about every possible cost and benefit under the sun, but focus on those that are most relevant for the particular problem or question that we're asking. We're going to place those variables in our model, and then we're going to think about some exogenous variables, which might be appropriate to place into our model that would be helpful for understanding some of the predictions or making the predictions that we want to focus on. We will solve the model, I put that in quotes because you don't necessarily have to solve it in sort of the formal mathematical way. And then we will simulate or derive predictions. So our running example here is about changes in social interactions during the early part of the COVID-19 pandemic. And so the figure on the right, which comes from one of my papers, shows a big increase in people staying at home starting in late March of 2020, sort of when everyone really started to get afraid and concerned about COVID-19. The question that I want to focus on is, why was this? What were the factors that drove that decision? What economic model can explain this? And what predictions can we derive from that model? So we're going to go through our steps in model building. What is the choice variable and who decides it? So individuals decide how much activity, I'm going to call that lowercase a, they're going to undertake. Let's think about some benefits and costs. On the benefit side, we have socialization, work, learning. On the cost side, travel costs and the risk of illness or death. We're going to focus in on socialization, which we'll call capital S, travel cost, capital T, and the risk of illness or death, capital R. And now we're going to write down our model, and we're going to write it down as a maximization problem. So we're going to maximize our objective by choosing an activity level. And our objective is going to be the benefit we get from socialization, S of A, minus the travel cost to socialize, T of A, minus the risk of illness or death, R of A. So we're sort of saying we can put all of these things on the same scale and then add and subtract them in order to construct an objective function that people are going to care about and that we can use to model and think about behavior. So getting this equation is really the key part of modeling, of model building. And let's think about some exogenous variables that we want in our model. So some examples might be, how many COVID-19 infections are there in the area? We'll call that capital C. How able, or are you able to work from home, right? What's the size of your family network, and some state policies, which we'll call capital P. So we can put them into our model and say, well, your need to socialize, your benefit from socialization depends a little bit on your ability to work from home. So S is going to now be a function of A and H. The travel cost is going to depend in part on state policies. And here I'm really thinking about stay-at-home orders. We can talk about other things later on separately. And our risk of infection depends on both our level of activity as well as COVID-19 infections in the area. And for that one, I like to do the thought experiment of, what if C is 0, right? If there's no COVID-19, then that risk function is 0. You can't pick it up if there's no one with it. So we think, for example, that the cost of, or the risk of infections going up as C goes up, and what happens as activity goes up, it should go up too, right? The more active you are, the more likely you are to get sick, you're more likely you are to interact with people who are sick, etc. We can think about the same way in the travel function, right? So as activity goes up, you're doing more travel, it costs more. As policies come up that restrict or attempt to restrict mobility, that will also increase the cost of travel. And we've already talked about a little bit about S and how H might show up in S. So now we want to solve the model. And so we have this maximization problem, and traditionally we would solve it by taking a derivative with respect to A to say, okay, well, what level of A maximizes this net benefit? So we can show it here as, the partial derivative of S with respect to A minus the partial derivative of T with respect to A minus the partial derivative of R with respect to A, and we're going to set all that equal to 0. That's sort of when we're at that peak of this net benefit function. And what this says is that the increase in socialization, the increase in that socialization benefit from a marginal increase in A is going to equal the increase in the travel cost and your increase in risk from increasing A. So, and we can also solve this graphically. And the way I would do that is I would recognize that embedded in this is a supply and demand model. And in fact, in the paper that I wrote, that's actually how I did this. I just laid this out as a supply and demand model and said there's a demand for social interactions, which is S of A, and then there's a cost, which is T and plus R combined, right? So minus T minus R, that's the total cost of these social interactions. And then you can say, okay, well, that's there's a marginal benefit curve, which is going to be downward sloping like this. There's going to be a marginal cost curve, which is going to be upward sloping like that. And there's going to be an equilibrium. Now, we did all of this to simulate or derive predictions from the model. So let's think about some predictions from the model. What happens if we increase C? Well, that's going to increase the risk of infection. So that's going to make our initial level of A, right? That level of A that we would do if there were no risk of infection. Well, now we're going to be getting negative value out of it because R's gone up. So what do? We need to reduce activity to compensate. So we have a prediction that as the risk of infection goes up, so as C goes up, A is going to go down. And that's our first prediction from this model. What about if we increase P? So if we make the time cost of travel or the travel cost higher by increasing P, that's going to increase the overall cost of travel. And again, we need to reduce A to compensate. So the key predictions from the model are that there's going to be less mobility when COVID-19 infections are high or increasing, and there's going to be less mobility when state policies restrict mobility. So thinking here about stay-at-home orders and things like that. And you will be doing this over the next 2 weeks in PackBack, and I wish you lots of luck.